Everyone, what we'll look at today is oscillations of masses on the ends of strings. Not springs, but just having something swinging back and forth on a string, and how we can relate that to what we've done before with simple harmonic motion. If we look at a simulation of this, in order to get this mass in simple harmonic motion, I'm going to pull it back from its initial location a certain degree, and when I let go, the mass will oscillate back and forth from amplitudes, go through an equilibrium, and go back to other amplitudes. Just like a spring and a mass system, we do see similar things with this, and we can time the oscillations to see how long the back and forth motion takes. So in this case, it takes about 2.8 seconds for this pendulum to oscillate. It is a 2-meter pendulum with a mass of 1 kilogram. Things that you could change that you did in the lab today is we could change the mass. So I'm going to make that mass larger and time it again. .84 again. I'll make the mass smaller. .84. So it looks like mass has no effect on the oscillations of a pendulum. Well, what could affect the pendulum? Let's change that length. Let's make the pendulum longer. Now it's 2.5 meters long. And if I time that here, it does take a lot longer for that pendulum to oscillate back and forth. If you think about it, it's got a further distance to travel, distance meaning arc length, when we're at these longer radiuses. Let's shorten that pendulum up. Only 1.4 seconds. So it does matter with length, just like a grandfather clock has that long pendulum swinging back and forth. That is what they use to time each second for your oscillations. So it has nothing to do with mass, has everything to do with the length. So let's write out equations for forces on a mass that is oscillating back and forth like this. Well, if I wanted to analyze some forces, the obvious first force is gravity. Gravity is always trying to pull that mass straight down, and since we're at an angle, there is a tension. So if you look at that setup with our tension and gravity, we can tell we are unbalanced, and we're unbalanced in this direction that is heading back towards equilibrium. If we make that angle steeper, that force is going to change with the displacement that we do, and this follows simple harmonic motion. Remember, simple harmonic motion says that the acceleration must be proportional to the displacement. And we're going to travel a larger displacement if I pull that further back. So this is going to follow simple harmonic motion. So let's write out the forces and the formulas to get this oscillation. So in looking at this, we've got tension and gravity again, and the force that's going to cause us to come back to equilibrium is this component of gravity. Or if you wanted to break it up with the tension, you could figure out which part of the tension is actually pulling the object forward. So really we could say that mg sine of theta makes our mass accelerate. Now, the displacement, since we're talking about a linear acceleration over here, that linear acceleration is going to follow this arc length back to equilibrium. So we have to write our acceleration in terms of arc length. So really, instead of ma, I want to write d squared s dt squared, the second derivative of our displacement with time. So s being our arc length, that's the distance we're traveling. Since we're traveling in straight line, well, we're trying to travel in straight line motion, the string is going to cause us to follow that arc. So this bolded line here is our arc length, and as we sweep out that arc length, we know that we're also going to sweep out theta, and the relationship between theta and arc length is s over r. R in this case is going to be the length of the pendulum, so instead of s over r, I'm just going to write it as s over l. And on this side, I still have mg sine of theta. So first thing I can notice is that the mass does not matter. Just like we showed in the simulator, I can get rid of the mass, and any mass will oscillate back and forth at this particular length. But then if you look at my restoring force, it's now in the terms of g sine theta. And on the other side, I'm talking about linear displacements of ds over dt. So let's try to translate the arc length into thetas so we can talk about just this angle changing rather than the arc length changing. Or to get rid of the ds, I'm going to solve for that and get theta L. So taking the second derivative of arc length will also give me the second derivative of theta, and there we go. We now have the second derivative of theta with respect to time, which is our acceleration back towards equilibrium, multiplied by the length of the pendulum equals g sine of theta. And if I want to get just acceleration by itself, I can get rid of the length and divide the L over. So again, my acceleration is going to depend on two things: the gravitational acceleration of the planet I'm on and the length of my string, which we said the length was known, but the g was not known. So let's solve for that acceleration. So the angular acceleration here is going to equal g over L sine of theta. Now one thing that we want to do with this and translate this into simple harmonic motion is that we can say that the acceleration that we experience when you pull it back a certain distance from the amplitude, we know that the maximum acceleration from equilibrium is equal to omega squared times the amplitude. And since we now know the acceleration from our forces, our acceleration is g over L sine of theta. So just like we did for the spring mass system, we can set these two accelerations equal to each other. And I know I have regular acceleration there, but regular acceleration or angular acceleration for something in simple harmonic motion would still be the same. It'd be omega squared a times cosine of some function if I wanted to stretch out my whole thing. But all I'm caring about here is the maximum acceleration. Now there's one thing and one little trick to the pendulums that you want to do. We want to pick a small angle. And why do we want to pick a small angle? Well, say you pick around 1 degree. So if I put in sine of 1 degree, sine of 1 degree will spit out a number to you. Try tangent of that 1 degree. See what number you get. Also, even try converting 1 degree into radians. And what you see in all three trials here is that the sine of a small angle, the tangent of a small angle, and 1 degree turned into radians are actually all about the same number. So as long as your pendulum is pulled back a small angle, you will have the same whether you use sine, tangent, or just translating theta into radians. So let's do that. Let's translate theta into radians, which means that I can just replace sine of theta with theta. And now I have an acceleration equation for my theta with two constants, g and L, and I have a maximum acceleration for things in simple harmonic motion. Since we have those two accelerations, let's set those equal to each other. So g over L times theta will equal omega squared times our amplitude, and the farthest back we're going to pull this pendulum is going to be that theta. That theta is going to be my amplitude. And if you look on both sides, I now have theta, so I can get rid of my theta and just be left with omega squared g over L. So if I want to know the angular frequency of a mass and string system, it's just the square root of g over L, the gravitational acceleration of that planet and the length of your pendulum. When you want to translate this in the time periods, remember that omega is 2 pi over the time period. Our frequency is the inverse of the time periods. You could write equations for the time periods and frequencies. And there's your time period. So your time period depends on the length, and it also depends on the acceleration of your planet. The longer the pendulum, the longer the time period, and the higher the gravitational acceleration, so if you're on a planet that has more gravity than Earth, that time period is going to shrink. And you can play around with that and look at all the ratios of people say, well, one pendulum's twice as long as another. It'll give you the exact time difference from one pendulum to the next. So around the 24-minute mark of this frames of reference video that we talked about earlier in the year, this is the part where they talk about a pendulum, and specifically a Foucault pendulum. A Foucault pendulum is one that oscillates back and forth with the rotation of the Earth. So they give you a really cool demonstration to show you why a pendulum swinging back and forth eventually starts to veer off from its straight line path into this angled and curved path. So it all has to do with the rotation of the Earth and your frame of reference. We're on the spinning Earth, so that's why we see the pendulum move, but look at what they say about your frame of reference fixed with the stars. And this is another proof of us knowing that we went to the moon. Looking at an astronaut bouncing around on the moon, they had different things swinging from their belts. So as they stopped their motion from moving from one place to the other on the moon, people watching this on Earth could see, say, their belt or a hammer swing back and forth from their hip. When it swung back and forth from their hip, they could time the pendulum, and when they timed the pendulum, they actually would solve for the gravitational acceleration of whatever planet they were standing on, and what they got was the acceleration of the moon. So a very subtle thing that you couldn't fake if you were trying to do the moon landing in a studio. And the last little thing here is they say, well, how can pendulums show us if we're in accelerated frames or not? And again, it deals with your frame of reference. But again, if you look at this, you can see that here are the two forces on a pendulum. The pendulum was hanging straight up and down in that train car, and then the train car took off. If the train car takes off forward, we know the pendulum will want to remain where it was and swing backwards. When it swings backwards, we can analyze forces and say that, okay, my y forces here, Ty is equal to mg, and Tx is going to make me accelerate. So that's a very simple breaking up of our two forces, but we want to relate our tensions to the x and y components. So I could say that, well, the Tx, looking at my angles here, is the sine of that angle, makes us accelerate, and Ty will become T cosine of that angle. Well, if I wanted to solve for my acceleration, I don't know the tensions, or I don't know the acceleration, so we substitute and solve. Or what we could do is take T would be mg over cosine, throwing that in here for my x forces, I get mg sine of theta over cosine of theta equals ma. Getting rid of my masses and seeing that sine over cosine is going to give me tangent. The acceleration of my accelerated frame is going to give me tangent of theta multiplied by g. So if I measure the angle that a pendulum swings backwards when I'm in an accelerating frame, I can actually figure out the acceleration of the system that I am in. If I'm in that train car and the pendulum starts to swing forward away from me, I know I'm decelerating because the pendulum wants to stay in motion. And if the pendulum would swing left or right, I would know that I am turning, and I'm turning opposite the direction of where the pendulum would be swinging. But down here is a way to solve for the magnitude of your acceleration in an accelerated frame. One last application for periods with pendulums and masses on strings is a scene from Star Wars here, where you see this little Jawa fall off of its giant animal that it's riding, and it swings back and forth with periodic motion. So I'm going to provide a timer for you, and the fact that a Jawa is about 1 meter long, so I'll put some meter sticks in here to show you how long the string is for the oscillation, and go ahead and see if you can calculate the surface gravity of Tatooine. Good luck.